Good morning. Today's lecture we have a guest, Giorgio Marfella. He's the coordinator of applied construction. It's a subject you'll find at the master's level at the MSD. And his area of expertise is high-rise construction. And he's going to talk today about waterproofing. It's probably also a bit of glass and curtain walls. So please join me, and thanks, Giorgio, for being here.
Thank you. Okay, welcome everybody. As Alberto mentioned, some of you might see me again in the future, whether it's going to be, if you're going to stay in this school later on. I teach also in the construction management program. Today, I would like to talk about waterproofing from a perspective of construction, but also from perspective of design. So, because I understand this audience here will be a mix of future construction managers as well as architects, mostly. So by all means, we go through some of the principles, if you like, that will allow you to tackle an understanding of waterproofing from a designer perspective. But those principles by all means will be also transferred to contractors, okay? And then I'll conclude with curtain walls, which somehow are an area, we will not go too much in detail about that for a scope of this subject where you're doing mostly residential construction. But I will just touch on the aspect of curtain walls as an example of how somehow that typology was heavily influenced by how techniques for waterproofing have evolved historically. Okay, so it'll be a fairly condensed conclusion. And as usual, we'll have a break during, is that right, Alberto? Probably somewhere midway through. So the principles. Okay. Look, waterproofing is not a science, so that you might find there's no such thing as waterproofing engineers out there. Well, there is engineering, there is science associated with it, but unlike structures or mechanical services that normally have a figure that is somehow responsible for that particular aspect of construction, waterproofing is an area where almost nobody and everybody is equally responsible. Okay? So this first part will take you through some of these principles that somehow constitute a bit of a theory of waterproofing, if you like, which is shared and acknowledged in the industry. And before I do that, so please, there will be no formulas. It's just very simple concepts that everybody can remember. But they are exactly those concepts that will allow you to resolve waterproofing problems or to prevent them in construction. So first of all, when we're talking about waterproofing, we're not really talking about the same level of waterproofing you would expect to something that is submersible, say, under a liquid like a submarine. So we're talking about more strategies for weatherproofing, if you like. It will be a more correct aspect. But somehow the waterproofing aspect has to relate with water, obviously. Now, the natural inclination towards, the diagnosis of a problem would be to think about water as rain. And that's fairly true. Most of the times, waterproofing problems are driven by rain. However, bear in mind that water can also change its status. It could be vapor in the air that somehow becomes liquid water that can create problems. An area that is often forgotten is water source as from mechanical services too. Okay. So water is the element that somehow causes the problems, but then there's another element that has to come into play, and that's the forces that will somehow contribute to the fact that water may find its way inside a building. And obviously, gravity is the main one. Wind. So you have an expectation that water typically flows down, okay, from a high point to a lower point. However, don't be mistaken by that, because you'll find situations that are the reverse. Water can also climb up as a result of capillarity. Or if you have a very tall building, you'll find that the effects of wind are so prevailing that water will hit the building and the wind will push water up. So it's not necessarily always true when people say, well, water will always go down. Yes, typically, in a house, perhaps, but things can get quite complicated. Now, the science I was talking about before, imagine if you have a theorem, okay, like in maths, where you say, well, in order to have a waterproofing problem, you must have at least 3 conditions to happen. And these conditions are necessary. Okay? So in other words, if one of those is not there, the waterproofing problem does not occur. So these are the 3 conditions up here. Let's go through them. So the first one is kind of obvious. Okay? In order to have a leak or a waterproofing problem, you must have water. Now that sounds, ridiculously obvious. However, remember, water may be where you did not expect it. Water may be coming from surfaces. Water could be the result of condensation. Water could be going up when you're expecting to come down, etc. Okay? So you have to be able to understand that water can come from different sources. Second one, equally obvious, you've got to have a gap of something, like a break through the building that will allow the water to come through. Fairly simple to remember. Third one, you must have a force that will take that water from the outside inside. Now, this seems very, very silly to some extent. However, waterproofing are a huge problem in buildings because people actually don't understand how to relate this to construction. Okay, so remember, these are 3 conditions. They're all necessary. If I eliminate one of those, I don't have a problem anymore. So I've got to have water, a gap, and a force that takes the water through the gap. When I'm saying a gap, I'm saying any solution of continuity in the building envelope. Okay? So in order to resolve this problem, technology normally in building is organized in ways that will prevent one of those 3 things to occur. Okay? So there'll be waterproofing strategies that would reflect either the principle of eliminating water, the principle of closing gaps, or the principle of neutralizing the forces that will take the water through. So that's where the definition comes in handy, if you like, because suddenly you have an understanding of what you can do to minimize the problem. Now, the good news is that if you just somehow resolve one of those 3 issues, okay, the water, the gap, and the force, just one of them, you actually have achieved the result. The water's not going to go through. But it's easily said, but when you're detailing, things can get a bit more complicated. So some statistics also, just to remember. Remember that waterproofing in reality, it's a bit of a all or nothing kind of field. A building, if it's leaking just a little bit, it's not acceptable. Okay? It's not acceptable that a building might have just a tiny leak. Oh, it's just a 1% leak through the roof. No, a leak is not an option in the building. Okay? And you will find that most of the times these leaks occur in very, very minimal areas of the building envelope or of the roof. And those very minimal areas are the ones that somehow will cause the building somehow not to fit the purpose. So this is the complicated part of it, if you like. Is that, okay, I have a very simple theory. I can just do those 3 things, get rid of the water, get rid of the gap, and get rid of the forces, and that's all fine. But because you have very limited areas that could potentially fail, you've got to have an absolutely 100% quality control over the building enclosure to make sure water stays out. And this is where somehow the theory needs to be backed up by backup solutions. So in other words, I can have a strategy that says, okay, I'm going to eliminate the water by washing it away or doing things to get rid of it from the joints. But you have to have in place also alternative methods to back it up. Why? Because there's a human error factor, which is typically at the point where, say, 2 materials come together, at the points where 2 trades on site will start to interact with each other. And those will be the points where you're going to have troubles, typically, okay? One other thing to remember, that waterproofings are not a problem of failures of materials or components. So in other words, membranes, flashings, they're not things that normally will come in faulty on site. Far from it, rarely. Okay? It may have been initially for some materials, but typically they will do the job for what they've been manufactured with. The problems occur at the intersections. It's at the point where the membrane terminates, at the point where the flashing is adjacent to other materials that might not get along with. It is a problem where, for example, the trades do not install things properly. And this is what makes waterproofing, as I was saying earlier, not a science, but more a practice. And then it's a practice that is shared by different parties. So with this picture in mind now you can look at several detailing problems, solutions, and typologies, and understand them according to these three principles, okay? So I'll just skip through some of these options, and I've organized them in such a way that now you can look at them as strategies, either of those that will keep water out, or the ones that will keep the gaps closed, or the ones that will neutralize the forces, okay? So by all means, this is not an extensive, list of all the possible solutions, but let's have a look at the ones that keep water away. Diversion, a wash, a roof, okay? So you have when we say we eliminate the water, we can't let water evaporate, but in a building, all you have to do is make sure you take water away by following things towards plumbing, and the plumbing will literally get rid of it. It will get rid of it, with downpipes, gutters, etc. That's at sort of a micro scale. So if you look at a building overall, a 1 to 50, but when you're looking at details as well, you'll find that windows, sills, thresholds, parapets will also respond to the same rule. They'll have falls, they'll have almost negligible inclinations of their surfaces, so you can actually eliminate water from the surface. That's the principle of diversion. You do not want water to sit and pond over building elements. Okay, so obviously the slope will take water away, either inboard or outboard, depending on the scenario. Okay, and things can take complicated shapes, so that you can have, again, a combination of, say, a curtain wall, like in this case to the left, that may have very complicated extrusions. But you see, the morphology of everything in that extrusion is being determined in order to perform very specific functions in waterproofing. So there's two extrusions that come together. One of them has a fall that will take water out. There's a parapet cladding that sits on top of it that falls back in. Right? There's a roof, there's a membrane, etc. Now, washing away water, it's easy enough by inclining things. However, there's a few things to consider. Typically, these things that are on a fall, typically, not necessarily, also concrete parapet can have the same, but typically they will be metal. Right? So when you have water flowing from one metal to another, there's things to bear in mind, and they're about the compatibility of metals. Some of you may be aware of galvanic reactions between metals. So what happens is that metals by themselves, because they're highly reactive materials, if they put in contact and with the aid of water, they can create a current of energy, electricity, that can somehow activate corrosion into one of them. Now, metals corrode by themselves, even just in contact with oxygen. Steel is an example, it oxidizes by itself. Aluminium does that too, and it does it in a good way. It creates an oxide that does not rust. It's an oxide that protects it by itself without any coating. Then you can also coat it, but it does that. The problem with galvanic compatibility is the fact that if you have two metals in contact with one another, you can have this kind of situation. The two metals sort of establish between themselves who's going to be better than the other at rusting. And one of the two metals will rust and pick up the rust of the other one. So the other one remains absolutely protected from rusting, but the other one catches it all. Okay? And there's a hierarchy there. So for example, copper is one of those materials that will just make other materials rust in contact with it. Okay? It will just basically get rid of my rusting, and I'm going to give it to aluminium or steel or whatever I'm going to be in touch with the help of water. So this is contact, okay? But if you also imagine water flowing from one parapet, say, to a gutter of a different metal, you can also have that problem. So there is issues of compatibility. Okay, so it's not only about shape. Diverting water is also making sure that things somehow are compatible. So this is from the Australian standards about water, 3,500 actually. It's not the waterproof, it's a plumbing standard. And these charts, I put them here just to give you an understanding of the fact that there are expectations for metals to go together or not. So for example, aluminium is a fairly friendly material that has good compatibility with most materials, but not with concrete and mild steel. So you'll need to have separation barriers or so. Copper, on the other hand, is one of those materials that if you were to think about a copper roof, well, it wouldn't be enough to have just the roofing copper. Also, all the plumbing, everything else will have to be of that material. Otherwise, you'll have galvanic reactions and accelerated corrosion of the other materials. Now, lead is also a very negative material, but lead typically is not used in building anymore. So that was one thing to put aside, okay? We're still talking about washing, diverting water from surfaces, from high levels to lower levels. Now, you can also imagine, as a designer, you can play with the tilt of these surfaces and make things somehow more manageable or less prone to risk. So this chart here, somehow it gives you a spectrum of solution in design of roofs where, say, at the top, you can have roofs that can go fairly steep and sloped. And obviously, the steeper they are, the quicker they get rid of water from the surface. So they wash quicker water away. So they respect that first principle, get rid of water from the surfaces of buildings. Now, the steeper the slope, the more permeable they can be. Okay, so thatch roof, for example, which is very common in England and in Northern Europe, but also in Bali. It's not a permeable material. It's actually so it's not impermeable, it's actually highly permeable. So how can it be used for a roof? Well, it can only be used on the condition that you have very highly sloped surfaces. Okay? Conversely, if you go down the path, if you follow that wheel in the other way, you might find that materials that are set on a flatter slope, they need to be absolutely impervious to water. Okay? So membranes will be the kind of thing you'll be looking at for a flat roof. So the plumbing is about conveying water into gutters and downpipes. And typically, you'll find that gutters tend to, the normal scenario is for, say, a building. Look, this might be like a childish drawing, but there are buildings that are exactly like that. Remember, so the steeper is that slope, the more permeable this. So if this is tiles, that's good news. I can have tiles because provided that the roof slope is quite steep. Now, the other problem is that what are we going to do with the water that comes to the edge? Now, typically, you would say, well, we'll put a gutter on the edge. We call that an eave gutter. Now, that's all very nice and true, but there's other problems when the architecture, and that's a very common scenario these days, when the architecture is like that, when the architecture is a box. So what are we going to do with water? Well, there is still a roof somewhere in there, and there is still a gutter, possibly concealed. The slope may not be exaggerated, as I said. But what this slide is talking about those kind of gutters, okay? So we call a box gutter. So you have a gutter that is somehow concealed behind a parapet, okay? There are some rules to remember about this, okay? First of all, gutters are not simple trenches, okay? They have that principle of diversion of water within themselves again. So they have fall inside them, And they need also to allow for pipes to come through, which they would also fall at an angle, okay? Okay, so these are design factors, very important for architects. Okay, understand the plumbing, understand that water does not have to sit still anywhere, okay? From the roof slopes, hits the gutter is also slope, and the slope to downpipes. Then those downpipes will go somewhere else. They'll go through the roof, they'll go inside ceiling spaces, and they will have a fall because they need to divert water away. So there are some elements that have to be put in place there, like the sump, for example. What is the sump? Well, it's an area of the roofing that allows for that extra capacity of water during flash flooding, for example, right? To convey water, to make sure that somehow that water is not going to get jammed here just before the downpipe and build up, potentially creating leaks, or my parapet could be a lot lower than that and just pour on the other side. Okay, so there's a sump, there's a downpipe. The sump is like a tank, if you like, that it's in correspondence with the downpipe. That gives you an extra backup. And then there's an overflow. There's an overflow also, typically there. So I'm going to draw that a little bit bigger. So this is the parapet. That's the sump. That's the downpipe. But there's a third element to consider there, and that's basically a tube that will come through the parapet to do what? To get rid of water and spit it on the street? Is that what it needs to do? Well, yes, but only if that somehow fails. If that's blocked, we have a backup here that will allow the water to come on the other side of the parapet. Why? Because remember, the box gutters are concealed behind the parapet, so they're not visible. They need to be somehow backed up by another solution. So it goes back to what I was saying before. Yes, you can waterproof following those principles. They're always those, but you're going to have strategies to back up if one thing fails. So here's an example. Okay, so that's the water. There's an overflow there. This is just some of the same views from the Australian standards showing you what happens in section. So you can see the box gutter always has a fall. The overflow has to be set at a certain height. There are some solutions here on the side that contemplate also the scenario where it might not always be possible to have an overflow because you might not have a wall onto which to punch through and spit out. So it could be in a scenario where, for example, let's say you have a building like that. It's a continuously high wall. Your box gutter is here, okay? Okay, so that could be a continuous wall. And we could say, well, and you have maybe another wall going that way, and I have another wall on this side. So we're sort of surrounded. We have no way of putting an overflow. Well, in that case, the solution is to have a downpipe, normal, which will be working most of the times. And another downpipe that is more like, like a periscope kind of thing, so that water typically goes down here. If that is blocked, then water will build up, but catch, another pipe, which is a secondary one. So that's a way of also having an overflow, a backup. You need some solution, some sort of strategies to get rid of water in case things go wrong. Okay. So these are some examples of water flows. Okay. There is a roof, and there is an allowance for water to somehow spit out in case things will get blocked. Now, you should be fairly aware of structures as well at this point. I'll second here, architecture or construction. So when you have a beam that is simply supported, and there's a load on that beam, what happens to the beam? Can somebody give me a hint? It sags, correct. Yeah. So it has deflection. Okay. In this very particular case, two hinged, or say a hinge and a roller, it will sag. So you call that deflection, okay, or sag. Yeah. So now remember, we're talking about water now. The ideal spot for a downpipe, it would be here. I'm exaggerating the deflection, obviously. It's nothing on that order. But there could be scenarios where somehow the downpipes are put in a spot where actually, you know, you can have continuous beams. They may be doing that. So we put a downpipe up here. I know a simple beam is easy enough, but what about a continuous beam? It's sagging upwards. Now, so you may think that that's a good spot for a downpipe, but far from it. You've actually put it in the wrong spot because the beam is going up. So that downpipe will never catch water. Okay? So this is where the principles are very important. And this is where, particularly on larger projects, you have to understand that the engineers and the hydraulic engineers have to talk to one another. And you will find there are better spots to locate downpipes than that. Or, again, I'm exaggerating that deflection there. You'll find it's going to be in the order of, I don't know, depending on what material it is, would be what, a 100th or 200th of a span. Maybe a 500th sometimes. So it's not that. But if you're doing a flat roof, well, that could make a difference. Okay? So there might be other solutions where there is a build-up that is exaggerated again here. They'll have to take that into account. So remember, forces are also very important. So, okay, yes, you divert water, get rid of it. I just have to slope it, downpipe slope. That's all makes perfect sense. But what if I will tell you now, actually, you know what, you can have a drainage system that it doesn't have to have falling pipes. You can just have them straight. Do you think I'm just selling you a lemon? Probably, but the fact is there is actually a system, it's called a siphonic system, that allows you to have plumbing, roof plumbing, that, unlike this one here, that has a fall. Well, the siphonic system will be such that you could just go out straight inside the building. So we say, well, then you're not getting rid of the water. Then the water will be sitting inside it. Well, yes, if you think about gravity, but the siphonic system will work on another principle. They work on a principle that they fill the downpipes at full capacity to the point that they purge air out of them. And this creates a suction effect. They can literally empty the downpipes quite quickly by relying on the fact that there's going to be no air left inside them and there's going to be a negative pressure from one side to the other. So you're playing with forces again of nature. It's quite complicated to understand how they work, but imagine if you have a head. It's an hydraulic principle. You put a lot of water at the top of it. You let it fill over the downpipe. Remember, downpipes have got air inside, so that air is going to somehow put some reaction against that water. And in fact, typically what happens is that in a gravity-fed downpipe, you'll find that the air is still there. And what happens is that the water is just going to go and flow around the edges of the downpipe. And the siphonic system, you fill it up to the point that you put so much water before you let it fall inside the downpipes until you get to a point that this water somehow is going to push and push and start to push all the air out. So once it purges the air out of the system, then that system is working on a suction principle and it continues to flow. So it's a system that works fairly well on commercial buildings. The new MSD school has that, for example. So what is the advantage? The advantage is, as I said before, you can have pipes that run straight inside ceilings, but also it works more efficiently, so you can have less downpipes. Okay? And they can be smaller because their capacity is not relying on the fact the water is flowing around, the edges of the pipe, but it's actually using the full capacity. So this is one of those principles that somehow, works with those areas that are called forces in waterproofing, okay? Other strategies of diversion can also, going back to this house here, they can also use this principle. They use just simply, this is very different from the siphonic I just explained, okay? It's just the overhang, okay? It's very simple. You get rid of water where? Well, you get rid of it from the ridge, you wash it away, but you also push it beyond the line of the wall as much as you can. Yes, you will need gutters here, but instead of having overflows and things like that, you just, if they fail, they're just going to flood the street. And Florence, for example, works on that principle. You can actually walk on footpaths of Florence when it's a rainy day very often in some streets without getting wet. I mean, the overhang of the roofs is such that it protects the pedestrians. So what I'm opening up here is the concept of a drip. Now, that can happen at the scale of a roof, but it goes also to the detail. Okay? It will be that point like a window head, a window sill that will always want to terminate, for example, a window sill. Where should I put the wall? Should I put it here? No, you put it there. Okay. Now, that is a problem sometimes if that's too much because you're cantilevering out, but this principle is like that roof. Okay, so these very principles that apply at a large scale, they also apply at a smaller scale. They're not obvious. You'll bump into this very often, okay? So that replicates itself when you have a roofing that is just over a gutter, the same, with a twist. The fact that because you're dealing with surfaces that are very thin, you have a potential for that water to somehow climb back, okay? So you can have a problem called surface tension, where water tends to stick to materials if it's going over very, very thin layers, okay? Surface tension. So the trick there, which is why you normally also, you have a potential for that water to come up here and just climb itself back there, and which is why you will put what you call a drip there to make sure that that water is not going to, I mean, it's okay to climb along soffits, but to go up, it's a bit harder unless there's wind or some, significant forces that will push it up. So again, that principle applies to roofing, applies to gutters, okay? So it's all coming back together, the roof, the gutter, yeah? And overflows. So that's a normal downpipe here. That's a traditional way of getting rid of water. That is that second type of downpipe I was talking about before, the periscope solution that is giving you a backup in case that downpipe on the right will get blocked. Okay, so again, the drip, as you can see, it can happen here on the sill, it can happen on the window head, on a precast panel, but it's got to be there. It's got to be there somehow. It can take form in different ways. It could be an overlap, it could be many different things. So a way of expanding on this concept of the drip is also to have, overlaps in cladding. So you can have, for example, a weatherboard house. That also works on this kind of principle here, okay? And it keeps repeating itself. Okay, obviously it's fixed here first, then the next one comes up. But it's doing something else, a bit more sophisticated. It's called a lap, okay? So it's putting itself in such a way that water is not invited to climb up. So this can happen in a wall vertically, but it can also happen horizontally when you have, for example, a waterproofing membranes, sheets, roofing. Okay? You put a lap, but make sure it goes the right way. So again, diversion means also that at some point you'll have to have strategies to get that water out. That water is not necessarily rainwater, as we said. It could also be condensation, for example, in a cavity of a brick wall, which is why you need those whip walls. You should. Also, curtain walls, same principle. You can have water infiltrations there, which actually it may be a positive thing. It could be water that is actually allowed to be there by design, but it has to be out. Okay. So that was a fairly broad exposure to the concept of diverting water in detailing. Okay? It's not so much the hydraulics we looked at. We touched on some of those. So remember the second principle. You've got to have water. Second one is you've got to have a gap. Okay? So what can we do when we have gaps? Well, we can close them. We can zip them. Okay? We can seal things so that somehow we leave water or air out. So when you have a roof like that, which is the roof of our building, not this one, the MSD building, you have not a situation that is highly encouraging for water to fall out. Yes, there is a fall, but it's fairly flat, as you can see. Now, you see all that water there. It's actually not rain. It's just condensation in the morning. Okay? So there's a lot of water sitting there. Glass is a good material. It's impervious to water because in the mix there was things that have been added that doesn't make it soluble to water, which is good. It lasts quite long. Lasts for thousands of years. Okay? So glass is not the problem. The glass is the problem because it creates somehow the condensation, perhaps. But the problem is these lines here. Okay? So that's the problem where things have to be resolved, and they have to be resolved by sealing. So there is normally a silicone or a polysulfide sealant that is very strong. It's working by adhesion, and it's making sure it's zipping, if you like, all those glass panels, so there is absolutely no possibility of water to penetrating through. Now, because this is a flat roof, remember, so it's the principle. There's no chances to be taken here. It's going to be absolutely sealed with silicone, but also with gutters that could be on the underside. So what are these materials? What do they do? Well, they work, they are usually rubbery materials. That they work on a principle that they give and they expand. They're very elastic. They have a very low modulus of elasticity, which means that you need very little force to pull them apart. Okay? And they're designed to do that. So they're designed to give. They're not designed, unlike in structures, they're designed to resist. These are designed to let go. So the problem with these materials is that they are sealants. They are put by a person, normally applied with a gun. And they don't like to be stretched in all sorts of ways. They like to be stretched typically only in one way. So they work on adhesion. They have a perfect adhesion on two adjacent materials. But in the moment they touch other materials or they make contact with other materials on another side, they might start to tear apart. Okay? So for that reason, these sealants have a thing called a Becker rod, which is a sponge, fundamentally, that is inserted in the gap before the sealant. And that sponge allows for that seal not to bond except then with the surfaces of the material that you try to bond to. So, in other words, if you have a gap like that and you just fill it with silicone or polysulfides or butyl, etc., it's going to crack. Not because the silicone is not capable of being stretched, because getting stretched and it's also getting pulled in another direction, and therefore the seal will fail. Okay? So it's very important. There is always a bond breaking or a Becker rod, which is that thing you can see here. See this? They look like, pool noodles, It's exactly the same material, okay? It's a sponge that it's inserted in the gaps. And that has to be there. There's other types of backing materials or seals that can also work on different principles, like the EMS seal here. But they perform more or less with the same principle. They need to be able to stretch only in one direction and not bond with the front. The front typically is the area that is sealed, so it's not an issue. But typically, the potential problem is at the back of the seal. So these seals must be good. They must be done in a certain way. They apply by hand typically, if not on site in a factory. They're done by skilled people. And they can fail for many different reasons. They're actually not that reliable, okay? To the point that sometimes you have to have two of them, or as I shall conclude, you know, when we talk about curtain walls, or you just do not make the seals anyway, okay? So as much that they exist, they are necessary, they'll be in the construction industry forever, since we've you know, introduced all these plastic elastomeric materials, etc. They should not be relied blindly all the time. There are situations where they are inevitable, like in a glass facade, provided you need to fix the joint. But typically, these are, say, podiums on commercial buildings or applications where they're not necessarily a habitable space. They're not necessarily also at height. They'll be very often shaded under a colonnade, or they'll have some other means of protection. Now, I'll just let you have a quick break, and then we'll keep going. And we'll talk beyond seals. What else can we do to control water, okay? And we'll talk about forces. So just have a quick break, and then we'll come back soon. Let's continue in this discovery of solutions about keeping water out. Now, just to recap a bit. So, you have one option, okay, which is just to flush, if you like, water away from the building surface, from the roofs, etc. But remember, it's not only the bigger picture, it's also about the morphology of the components, how things come together. You're going to have overhangs, drips, etc. Now, then there's the other option, you know, you just close the gaps, seal them with silicone, etc. There may be scenarios where you can do both things and they work very well. There's a few other strategies out there that deal more with also forces, okay? They deal with the fact that you can somehow manage either gravity or manage capillarity and differential pressures in air, which is what we're going to conclude with, which is probably the most sophisticated concept in waterproofing. And you'll have probably time to discover that later on, but I'll touch base today about that too. So one way of dealing with forces, it can be by creating barriers, okay? So barriers, for example, against capillarity, against the fact that with porous materials, water will tend to find its way up through the pores of masonry, for example, pores of a concrete block, the pores of a brick. So anything that normally is in the order of a few millimeters small as a gap will have a potential to drive water in a direction that you wouldn't expect it to, which is upwards. So a sponge effect can occur. It's also very similar to the principle of a surface tension I touched before, where you have, say, a roofing that is cantilevering over a gutter, and you have a potential of that water to flow backwards. Okay. So the most obvious solution to this kind of problem is in the case of masonry, when you have to have the DPC, damp-proof courses. Okay. So what are they? They are strips of bituminous felt or a combination of aluminium, which is also, say, protected with other felts around it. And there is normally a strip of this material that is set at a certain height from the ground to prevent water to climb up. Now, this can be to code requirements. So you'll find that in Australia it's spelled out there in this standard, 4773. So what you have to protect is potential water coming from underground up, but also there's a problem of water splashing back on the base of buildings. So ground is moist, and so you'll have a potential of water going through the masonry by capillarity, but you also might have a hard surface against the wall, which is good normally for washing water out, but there could be water splashes that will also wet the base of the building. And to this end, this is where the damp-proof course in masonry occurs, okay? So there has to be a strip of material that acts like a barrier, fundamentally, for that water to stop. Where is the water going to go? Well, it's just not going to keep going up, and that's good enough. It's going to stay there and evaporate out. Obviously, the base of the building will have to be such that you'll have to allow for this presence of water to be there and to be get rid of. So if it's concrete, it's going to be concrete with additives that make it somehow more suitable. So if you're in a cold climate, you might find it's what is called aerated concrete, which actually has gaps inside that will allow the water to sit there. And in case, should it freeze, it will allow the water to expand without breaking the concrete, for example. In Australia, you probably wouldn't need that, but you will, unless you're in the Alps. But there could be other materials that have to be somehow water resistant to some extent, not necessarily waterproof. So this concept of the break can also happen, say, at the junction between two concrete slabs. So again, imagine that to be a concrete slab on ground. Like this picture here on the left, you will have a ground. And what you call a cold joint. So you have a slab poured one time, another slab poured later on, and that leaves a gap there, typically. So that gap could be sealed, close the gap. However, as I said before, you have a potential failure there. The gap could be subject to expansion. Concrete shrinks by default. So there is a serious potential there for that to fail, which is why normally before the cold joint is done, there are barriers that are put there in place, okay? So that water coming either from the top, mostly in this case from upwards from the bottom, if it's a slab of ground, it's stopped to continue. Okay. There is also different materials with which you can do this. So you can use, for example, rubber strips, but there can be also materials called bentonite, which is a material that it becomes waterproof, if you like, when it touches water, so to speak. It's not quite a waterproof material in itself. It's a material that when it touches water, it expands. And by expanding, it creates a barrier that is more efficient for the penetration of water, okay? And that's called bentonite. I'll write it down here. So those are still strategies somehow in order to prevent water to pass through a barrier. So you rely on the fact that there is not so much a seal anymore, but it's a surface, okay, it's a significant area of a building that can somehow block water to proceed further. It finds a wall and it just doesn't go through. It's a barrier, so that is impervious to water. It's just not going to let it through at all. But the water remains there where it is, okay? So that water that remains there will have to be washed away, okay? So the principle still remains the very first principle. Now, these barriers can be flashings as well, but they can be strips, but they can also be entire roof areas that could be covered with a membrane, okay? So membranes are those barriers that somehow expand themselves over a whole area of the building, like a flat roof in a terrace, for example. Okay, and just as an introductory sort of concept about these membranes, just understand there are fundamentally two types. Okay, there are the ones that are applied in sheets. Depends, could be less or more large, but normally these sheets could be rolled out, or they could be sheets that could be handled. Those sheets will have to be joined together, and they'll have to be joined together respecting the principle of a lap, which we described before. So you'll have to have sheets that come together like that. They have an overlapping zone, and that zone will have to be sealed. And so there'll be a seam. It's a bit like making clothes, in a way, with waterproof membranes. Now, if there are sheets that can be sealed, for example, with torches, so they could create like a weld type of connection, if you like, between the two sheets. So there's not only a lap, there's also a seal. That would be the case if you're using, for example, bituminous membranes. Okay. So imagine a blowtorch, and some traded skillmen who can do that, but also the conditions around where you can actually use a blowtorch. So blowtorches, as you can imagine, are not exactly a friendly thing. And to be used on site, there's issues of safety. It requires very specific labor requirements. So there's an alternative to that, to this type of materials. Well, there's the ones that can be sealed also with cold joints that may not require blowtorches. But there's also the possibility of using paints, if you like, that can act like a barrier, and those will be liquid applied. So they could be just simply rolled on paint mixtures that once they set, they are impervious to water. And they may have to have, obviously, a resistance to ultraviolet light in case are going to be exposed to the elements. Or they may also have to have some additional elements in the mix, for example, to prevent people from falling and slipping should they be exposed and practicable, okay? So they are a paint for a floor, typically. So these materials, bear in mind, they're always good for themselves. You'll find the manufacturers will have warranties. They will have also required applications that will typically support the designers or the builders by giving advice. But it's also very important that they are used properly and that they are installed properly by the right people. So they're an area that needs to be considered carefully at the design stage by everybody. This is an example of a liquid applied membrane and how it terminates against the parapet wall. So there would be a situation where, say, you have a flat roof. In fact, what happens there? This is a terrace. Just behind that, there's a gutter. And that membrane is just going up that way. And then there's a piece of metal that caps it where it terminates, because that's the weak spot. I mean, the membrane by itself is good, but at some stage we'll have to stop. And that's exactly where the water is going to go through. Okay? Which is why what I said initially, it's not about the material failing, it's about how that material is going to meet up with other things that normally creates the problem. So in this case, there is a flashing that comes on top. It's mechanically fixed to the parapet, and there's also, in this case, something that corresponds more or less to that kind of look. Okay, so there'll be a parapet also on the wall. Okay, so there's a termination like that. Then there's another parapet that comes this way, and look what it's doing. It's actually creating a drip. Right, so you see these things are all coming back together. Okay? It's always those. Don't invent anything new. Don't reinvent the wheels. These things have been used in construction for years with all different type of technologies. Okay. Okay. Again, a membrane hits the wall, has to go up. So it's a bit like this. It's a bit like a skirting. I mean, this is not continuous, they're two different materials, but the principle is like a carpet that hits the wall and you roll it up rather than stopping it there, okay? So what happens there at the curve? That reality is that that is a detail, but drawn, you know, like you would draw it, more or less. But the reality is that when the membrane turns, it's not doing that little kink or chamfer like that. It's actually curving up, typically. So, and that really doesn't make a huge difference from that kink. That kink is drawn like that simply for practicalities, because we inherited drafting convention from a time where hand drafting was the way. So to do a straight segment rather than a curve was always faster and easier. Now, there's a very important thing happening there, and that's a fillet of material that is like a bond breaking. So it's just, this is like the backing rod that we looked at in the gaps. It's a material that is there to make sure that that membrane is not attaching itself too closely with the corner. It's allowing that membrane somehow to be stretched without too many bad surprises. Because usually, again, these materials are flexible. They're like a sealant type of thing. They're rubber, normally. And again, you can push them in one way, but in the moment you push them also in another direction, you're asking for trouble. So if you want to cut an elastic, what do? You stretch it, and then you cut in the middle. You snap it in the middle. Well, the membranes are the same. In the moment you stretch them, they become weaker. Not if you keep stretching them. They're going to keep elongating themselves. They become weaker in another direction. Okay. But note also how it goes up. It returns up. It says there 15 millimeter minimum overlap. But there is a height as well of the return that will depend on the scenario you're in. The Australian standards will tell you what it is. Normally, don't expect that to be anything less than 100 millimeters. Okay? So there's a return up, and there's a metal cap or something that will go on top of it to protect its edge. So that metal cap, which is called a K-flashing, as you can see, it's got a little fold out to prevent surface tension to go up. And it folds up that way too, and then there's a sealant and a backing rod, or maybe not, provided there's enough. I will put the backing rod there too. So what are we doing here? We're making sure, okay, there's water here, there's a seal. So that seal is going to have to be good. You have to trust it. Right? But you might have another material, possibly a cladding that comes and protects that. That's good practice. Okay? So you don't rely on the seal to be exposed to the elements and do the job. You might have no choice in some solutions, but this is an ideal scenario provided that you have a cladding that comes and overlaps over that too as well. And this protects the termination of the membrane. Or alternatively, should you not be in a position to do this by having a material that overlaps to that, the other option is, say, for example, to have a parapet wall, a saw cut on this parapet. And so a slot cut in concrete, for example, continues with a chainsaw. So there's a little rebate into the wall. And this time the membrane can return up this way and tuck into that slot. Okay, so you tuck it in, and then there's a sealant there that also does that job. You can also put other things on top of it like that and protect it even further. Now, these kind of things are normally given by manufacturers. So depending on what product is used, you will have the recommended practice for terminations of membrane. So remember, it's not about the material, it's about the use, it's about the suitability, the application of that material for a specific condition. Okay? So as a designer, as a builder, you have to sit down with whoever gives you that material, who's selling you that material. They must have an answer for you when you ask how you're going to terminate it. But you must have an understanding in your head that that is a weak spot. Okay? Okay? School is going to be over once you're out there in the industry. Okay, so you've got to have a scenario in your head. You don't need to know the solution. You need to be able to spot the problem. And the problem is the termination typically up, termination against the wall, contact with other materials, compatibility, many different issues. Okay? Exposure to the sun. Okay? Another example. So this is some more about waterproofing. In this case, would be, for example, for a liquid applied membrane. So, okay, up stance. So far, we looked at the scenario where you hit the wall, turning up, etc. But there's also scenarios, for example, on door thresholds. The same principle will still apply. You have to make sure that the termination occurs in such a way that it's not exposed to water directly, etc. Outlets, like, for example, where you have, the downpipes, same. Normally, suppliers will have solutions. This is the Australian standard explanation of this. So in this case, the solution is to have a collar. So there's a hole in the concrete. And when concrete is poured, a collar is inserted into it. Okay? So that bonds with the concrete. And these collars will have, obviously, the right shape, the right thing. So for you to put what? Put a clamp on it. Okay? And there'll be something that can be screwed onto that clamp. Now, the principle here is that the clamp puts pressure between itself and the collar, and the membrane will come in through between. Okay? So it will just make sure there is a pressure connection there that wouldn't allow water to slip through. And an overflow, similar scenario, okay? Where you have water, liquid applied membranes that might have to, also engage with the overflow itself. Now, these are membranes we'll be talking about, but to some extent, I would say the principles also apply for flashings, which I'm sure you understand now. So instead of having a bituminous material or a stretchy material that can be applied over, imagine to have a metal sheet that has been folded and given a shape to allow water to either find a barrier or to find its way down through a slope and to be drained out. Okay? So flashings are a form of barrier, again, but they will respond to similar principles of everything we talked about so far. So they will have laps, they'll have drips, they'll have overhangs, they will have return and upstands shape that create basically an upstand wall that goes up. And they will create laps, for example, on a roof. Okay, so the typical scenario of a roof, again, hitting a vertical wall will normally have two flashing. Okay, they'll have a flashing that engages with the ribs, and there'll be another apron flashing that comes from the wall and overhangs over it, or creates a drip over it. They can also have shapes that overlap through cappings. Now, one thing to understand with flashings is that it might be tempting to detail, say, for example, in this scenario, wall, roof, you have a gap, you've got to close the gap, wash water away. So it might be tempting to draw flashings that do that in one go. But the truth is that flashings come in length and widths. Normally, they need to be broken down in discrete elements, okay? So there will be a scenario of that kind, perhaps. Okay, so I have flashing number 1 and flashing number 2. So that's the wall, okay. So please understand this as well. The flashings are not something that just runs continuously. They're always elements that come to size, particularly those that go around windows, etc. Okay. So these are simply, from manufacturers like Lysaght. Lysaght produces steel framing as well as steel cladding systems, so you can clad buildings with corrugated metal. The problem, obviously, is not the corrugated metal by itself, it's where that metal will interface with other materials. Skylights, another Achilles heel of the roof. So you can have a potential of a skylight that can lead water in. Now, what is the strategy on a skylight? Well, the good practice is to elevate the skylight over the roof line. So normal standard is to take the skylight, let it lift up around the roof, and then flash around it. Now, that's easily said because, it makes sense. You have a roof like that, as a skylight through. Well, the last thing you would want to do, given that water is going down this way, is put the skylight like that. Because you're not doing a skylight anymore, you're doing a gutter. So the water will come in here, sit there, and you're going to have a leak. So the only strategy really is to actually go upwards where the skylight is. Now, there is still a problem because water is going to hit that side of the skylight and stay there. It's going to be fine that way. But what that diagram shows you, particularly this one here, it's what it's called a soaker, okay? So there is a scenario that where water comes, hits the back of the skylight, and needs to be drained around it, okay? So have a look at that detail. It's quite interesting. But there are ways to resolve these things. And again, whip holes, same thing. So same things apply also to wall assemblies, where you can have water that somehow is washed out through flashings, with whipples. And I'm not going to, stay much more on that because you should know about brick veneer, I suppose, enough. So let's talk, to conclude, just more sophisticated systems, okay? So those are the very basic ones. They are the ones you will find in a residential building. And this is the kind of technologies, if you like, that you would apply instead more on commercial buildings, or which, by all means, they will still respect the rules that we talked about before, okay? So in a way, commercial buildings will expand and include these too, but they do not stay away from all that we talked about before. So the principle of the wash, the overhang, the flashings, they will always be there, any building, ceiling, etc. So these systems, they rely on the fact that you have materials that you can model and modify in their morphology to the point that you can somehow discourage water to go through them. So for example, aluminium is an ideal material because it's a material that has a very low melting point that allows you to extrude it quite economically and give it very complex shapes. So, in other words, you can create labyrinth shapes inside the components that can discourage water to go through. So the water finds a labyrinth and the water doesn't know how to go through it anymore. Okay, so this is the approach where you have, say, up there on the left, you have a no-labyrinth configuration where water may hit a joint. The joint is raked towards the outside. That's good. That's the way to do it because you want to wash the water out. But there is still a chance that there may be splashes of water that will go through the gap and bounce in. So the approach there would be to create what you call an overlap or an upstand, provided the material is workable enough to create a condition so you can overlap. Now, metals are usually good materials to do that, but precast concrete will allow you to do that joint just as well, okay? because precast concrete can be worked within reason, because there are limitations on the cover of the reinforcement inside that will prevent you to do things that are too fine. But aluminium can be extremely intricate in its shapes, and it can work very well in this kind of solutions. Now, precast, this is an example. Okay, so this is the typical joint between two precast panels. They have a rebate, and they have a rebate exactly for the reason we're talking about now, because you're trying to discourage water to find its way through that joint horizontally. Now, water typically goes down, as we said, for gravity, but don't forget about wind, and don't forget about splashes, etc. There's another solution, which is just to seal all the joints, but those joints necessarily are not always reliable. Imagine you have a very large building, and you have a lot of panels. Could be in the order of thousands of panels. And each panel normally has 4 joints around it. It's called horizontal joints, vertical joints, 2 on the side, 1 at the top. And those seals typically will be put in place by hand. So chances of making a mistake are quite high. And remember, 1% of failure, that is a problem. That's bad enough. You can't just say, oh, my building leaks only 1%. If it leaks, it's not good enough. It doesn't have to leak. So what solution can you then apply? And this is the conclusive strategy. And in a way, it's the most sophisticated of all. And it's the one that, for example, allows you to build quite tall buildings. Okay? Because this course here has taught you more or less about residential construction. But, as the more you progress further, the more you'll find situations that are a lot more complicated. Not that a house is not a complicated thing. In fact, according to the Australian Institute of Architects, a house is a complex building. Okay? But the construction system, in my opinion at least, are not very complicated. I mean, you're only talking about sticks of timber, you lap them, you put a nail through them. Concrete generally is limited to the slab, and it's just ordinary concrete. It's not going to be high strength. It's rarely going to be self-compacting. Precast panels could be used, but there will be, I don't know, I mean, talking about for a house, single house in particular, chances of using precast even, it's not very common. Commercial residential may take you somewhere else. But as soon as you go into a situation where you try to build upwards, okay, doesn't matter if it's houses, offices, or anything, there is a prevalent problem in structures which will be about wind, and there is a prevalent problem also in waterproofing that is not anymore about gravity, but it's about also water penetrating horizontally through the building or upwards through the building. Imagine that. So suddenly all our drips are not working anymore. Actually, they're offering a gap through which you can push water through it. So it will leak. Okay. So what is the problem here? Well, if you just zoom in this area, imagine you have a wall on the outside. You're up in the sky, somewhere maybe 100 meters above the street level. Wind can press on the facade. Now, if wind blows against something, it's going to create positive pressure on that zone, isn't it? So you're going to have air that's getting compressed against the facade. Normally, the inside will have a pressure that it's less, or in any case, it's going to be different than the outside. Okay? If the outside is too hot, the inside is going to be conditioned, and vice versa. So rarely you would have a pressure equalized on both sides of the wall. Okay? So if you understand a little bit about weather forecast, you know that when you have differences in pressure, that's when storms are going to come. So you have a situation where air is going to go from areas of high pressure to areas of lower pressure. It's going to basically expand towards there. So if you have a building that has a potential problem of pressure differential from one side to the other, you have a lot of air which is trying to go through that wall. And that could be exacerbated by wind, Okay? Now, with all the strategies we looked so far, we cannot wash because, as we said, water is going that way, it's also going up. So if we try to put overlaps, we can't put weatherboards there because water is going to go through the weatherboards and inside. It's going to very quickly get over the barriers. So the other option is to seal everything. Makes perfect sense. I got the gaps and I sealed them. I've got to make sure they're going to be sealed and I close them. But remember what I said before. Imagine if you have thousands of these gaps. Well, chances are you might have failures of these joints. If not at the beginning for labor or lack of quality control, you're going to have failures eventually. Because buildings move, because the sun is going to be on those joints, because things might fail. So in the moment you have even a microscopic failure of these joints, you have a differential pressure, which is noticeable, and you have a very small gap. Now, if you're aware of the Venturi effect, and when you have hair that goes through our throat, what's going to happen to the hair? It's going to accelerate very fast. So this is a recipe for disasters in reality. You're creating a lot of weak 100% points on the facade of the building for water to go through. So the only solution really to resolve this is what is called a pressure equalization strategy. Maybe not the only, but certainly one of the best, which is to build up two skins, one and two. And this could be repeating itself. Okay, so this is the inside, that's the outside, wind, water, etc. So what do we do with that gap? We don't seal it, we leave it open. You leave it open. So you say, well, then water's going to come through anyway. Well, not really, if you leave it open enough for that pressure to distribute itself in there. Because suddenly I don't have a force anymore. You see, that's the third principle we're talking about. I don't have a force that's going to take the water inside. Yes, well, for pressure, but I could have wind, just mechanical force that will still drive water through. It's true. But this is where there's a barrier at the back, which is waterproof, and it's going to take care of that and spit it outside again. So that's called the drain joint principle. Okay? Drain cavity or pressure equalization. So you're talking about spreading your pressure from the outside inside the wall to some extent up to a point where you can then control it better and get rid of the water outside. So curtain walls work on that principle. Okay? Curtain walls of tall buildings in particular, but not necessarily all tall buildings. Any building that is a significant amount of multis, or any building that could be even sitting in front of the beach, for example, might have a similar approach. It gives you two levels. So you keep the most of the water out. You have an area that is sealed, etc., but it's not exposed to the elements. Okay? So it can be controlled better. Okay? Now, this principle can also apply to a door seal, for example, or a seal on a window. So you will find that the best place to put the seals, for example, are not right at the front, but rather, if you can, depending on the form of things, at the back of a door. So if you want to put a door seal in your house, if you can choose, put it on the inner side, not on the outer side, if you can, depending on the scenarios. Because by doing that, you're actually creating a pressure equalization. You're creating a buffer zone into which the pressure from outside can distribute itself. Okay? So that gap somehow helps. And trust me, it doesn't have to be that big. It can be an almost negligible gap. It can be just enough. You need to let it, not as minuscule as the failure of that joint, Okay, so there is an allowance for water to come through. We're not saying the water will not go through, but if it goes through, we have a situation we can control better. Okay, so this principle applies for most walls. Even a brick veneer, somehow, almost accidentally, it works on that same principle because it has weep holes. And those weep holes actually can create a pressure equalization. Okay? Even weatherboard buildings, if they have sufficient air at the back, can also work on that principle. In fact, that's why weatherboard buildings, they have building paper at the back, don't they? What does that do? Well, that's a waterproof membrane. So you're accounting for the fact that water might go through. Or commercial buildings, same principle. So just to give you a bit of a recap, curtain walls in tall buildings, they have evolved basically historically following very closely the development of our understanding of waterproofing up until we got that. So today, we take this for granted, okay? But it wasn't too far ago that this was implemented. We're talking about the 1970s. And the building actually that implemented this for the first time was the World Trade Center in New York. Okay, so it's a fairly new system, but it's what makes possible today to have commercial buildings, for example, to be clad in curtain walls or lightweight materials. And I'll just quickly conclude, just showing you a bit how we got to that point, okay? Because it's a very, condensed historical, thing. Obviously, could be a lot more that could be discussed. But just imagine, first curtain walls. Let's look at Melbourne as an example. Okay, so we can have a parallel of the understanding of, in a specific context, which is the city we are in at the moment. So the first curtain walls, this is the Hume House in the 1950s in Melbourne. There were some of the very first buildings that were built using aluminium, lightweight material that was developed during the war to build aeroplanes. Very good relationship between, weight and strength. As I said before, low melting point, so you can work it to things that you can then fix glass against it, okay? Now, those buildings used to... How am I going with time? What's the time? It's all right. Those buildings didn't have any understanding of pressure equalization. So they used to be glazed like you would normally glaze a window, for example, in a house. But they also had other complications. They were clad with glass that at the time was what you call plate glass. So it was a method of making glass in those days where glass was drawn in sheets. Okay, glass obviously it's sand and fire. It's about sand that is being fired at something like 1600 degrees and reduced into a molten glass, to a liquid sort of honey of material that then it's rolled out and straightened into sheets. Now, the method of producing glass historically was more or less, according to this diagram here. So where you have molten glass at the bottom, and then they will be picked up vertically and taken upward through rollers while it cools down. So still hot glass that, as soon as you pick it up and lift it up, it's cooled down, so it's becoming solid, but it's going through a lot of rollers. Okay, so when it comes out of that process of vertical drawing, glass, it's not straight anymore. So you'll have a glass surface exaggerated that will look like that. If you look through some old buildings, heritage building, you look through the windows, you will find that ripple. And when you look through it, you will not see very well outside of it. You will find that the image is distorted, okay? So I'll just park this on the side for a second. This is the way the glass was produced. It's got nothing to do directly with waterproofing. But that was one of the key things as well that made a role into this evolution of the curtain wall, okay? Because at that point in time, That glass, in order to be reduced to be good glass that you could see through, had to be polished. So there was very expensive machinery after the glass was produced to reduce it to two flat surfaces that you could see through and without any optical distortions. Okay, so the materials were sort of there. Aluminium was catching up. Glass was also changed. It was in a state of very expensive materials that wasn't quite what you needed to do unless you went through very, very expensive polishing systems. Okay. Now, some of the first buildings to use polished glass in Melbourne were a building that's been demolished in the 90s, for example, the Shell Corner building that was designed by Skidmore, Owens Merrill here in Melbourne. And it was demolished for nothing, because then after that it remained in a vacant block for years. But there was other issues that were coming up with glass. Not only the optical distortion, some glass was breaking because of thermal problems. So yeah, aluminium frames, glass. Aluminium expands significantly, glass less, a quarter of that. So there was differential thermal stresses that were somehow caused by the way the glass would expand and find, for example, sometimes an obstruction from the aluminium frame. Then there was other problems like nickel sulfide inclusions that were discovered inside toughened glass, which is notoriously tougher and stronger, but in the process of toughening somehow creates some impurities in it that can potentially let the glass explode. Okay, so you have a fairly shaky period of time in the 1950s. We have glass that falls off buildings, glass that is expensive, aluminium that it's a good material. You can organize it in shapes that are somehow good for you to keep water out. But the aluminium wasn't always used properly. So it was used, for example, like in this case, to glaze, with a sort of like a cross mullion type of arrangement. Well, this is the outside, and this is the inside, and glass was put through there from inside because it's more convenient, so install it from inside. Now, seal, and guess what? These seals will fail. Silicon didn't exist yet in those days, so water eventually will come through. So you have a problem with materials and a problem with waterproofing, which goes back to what we were talking earlier today. Okay? The problem with waterproofing that was resolved by saying, well, you know what, then let's glaze from outside the buildings. Okay? So what you would do, now we're talking about tall buildings here. You have to build a scaffold all around a building in order to glaze. Put the glass in a pocket where the outside is here, the inside is there, and there's a bead that sits here. Okay? Then there's a sealant at the back and a sealant at the front. Now the sealant at the back is protected from the elements. That will last. The sealant at the front may even fail. But actually, if that bonds sufficiently, it's enough. And what have I done there? Accidentally, I've created a pressure equalization scenario. Because there's a gap here, there's a zone here where water can drain out should it go through. This was ICI House. ICI House, you know this building? It's the corner of Spring Street and Lonsdale. Yeah? It's Nicholson Street. It's called the Orica House. Now, that building was built in 1957 to 58, and it's still using its original curtain wall. It does not leak because it was done that way, accidentally. For other reasons, well, because they said, well, we're going to glaze it from outside. And they built a scaffold around. They had to scaffold all around the building. A worker died in the process because it's a tall building. So you can't scaffold around skyscrapers. That was the limitation. In fact, that building is tall, 84 meters, significantly tall. But not like the tall buildings we'll encounter, and not like the ones we're building today. It's quite normal now in CBD Mall to do 200 meters tall towers. Do they have scaffolds all around? if you look in the skyline? No, they don't. So they glaze from inside without scaffolding, but they need to do something like that, right? So in the meantime, other things came through, like neoprene. So there was gaskets of rubber that could somehow seal the gaps more efficiently than sealants, but they were still relying on the fact that you're closing gaps through the building. Other things happened in the meantime. So there was pre-glazing solutions, prefabrication, where you could do all the pre-glazing with neoprene gaskets outside in a factory, ship the things on site, and install them from inside with that principle. But still, the building had to be then sealed with a gantry that came from the top in order to close all the gaps. So there was still a requirement to go back to the principle of closing gaps. Other solutions were developing in the meantime. So glass was kind of faulty in the meantime, okay? The solutions of pressure equalization were not understood, but the principle of draining with falls, collecting water, were there to the point if you go to St. Kilda Road, you find some very interesting building there. We're trying to manage water by transforming the facade into a system of plumbing for collecting water. Very interesting, you know, very ingenious ways of getting rid of water from joints. Why? Because the joints could not be trusted sufficiently, okay? Not to mention, obviously, other problems like, you know, movement of buildings. So from the 70s, there was also introduction of systems that allow you some movement. And then the World Trade Center came in. That introduced this principle. So the pressure equalization. Suddenly, you had a building that was so big that you couldn't possibly come later on and seal all the joints. And a solution was found to do it in this way, by creating a barrier from the inside and the outside that lets air distribute itself inside the cavities. So water is not sucked inside. Now, that principle was used in aluminum, but also was used into precast concrete panels. Same idea, same principle. And then glass finally sorted itself out. Okay? Then the float system of production of glass was done, which allowed you to have glass that, first of all, doesn't need to be polished. And there was other systems as well that minimize the risk of spontaneous breakage as well. So you get to a point, basically, which is not so far in time, when you have a convergence of different smaller innovations, which was the 1980s, the early 1980s. Rialto. Suddenly you have reflective glass, knowledge of waterproofing by pressure equalization, materials that do not break by themselves anymore, methods that would allow you to install from the inside, outside, etc. So those are the kind of strategic, things that have been done, and that allow you to have today systems that somehow work with that waterproofing principle, but they also allow you to build building upwards and from inside without dangerous scaffolds. So this is a bit of a recap. When you go from the stick systems to panelized systems that are not requiring scaffolds, there's also innovation in controlling gaps in buildings and allowing movement. The pressure equalization is critical. It's that moment that allows you to have panelized systems without the need to have to come back and seal them from the outside. And this is today very much, okay? From that point onwards, there was still a 60s stick system, not so much, the point of the system we use today, which are unitized. But you can see here, our construction rate in this city has skyrocketed. Once you have all these technologies, you can manage them. Then suddenly you can take the risk and say, I'm going to go out there and try to build a skyscraper, even without knowing who's going to be my tenant. Okay. So remember, waterproofing is very much a matter of risk control, and we're actually quite lucky. We have a bit of knowledge about it that we can minimize the risk. But it's for you to understand this knowledge, not in its application on every single project, but in its principles, okay? So the principles are to put together things without relying on very expensive, manual joints, but rather in trying to panelize things and install from inside out, okay? So with this one, I'll just leave you there, and thank you for your attention. Okay? Thank you.
Oh, then I hope to see a full room next week. We'll talk about the exam.